This is part 2 of section 1.2. We're talking about graphing functions, and this one just gives us a window into how shifts work for certain functions. What happens if you throw sort of like a scale factor in front of a situation like this? And what's going on when you have like a fractional exponent applied to some kind of shift? Number 17 on page 24 shows us a square root function that seems to have a 2 in front of it. So I'm just going to talk about it like this. Here's the square root of x. 0, 0, 1, 1, root 1, 1, 2, 3, 4, square root of that is 2, and so on and so forth. You go to the perfect squares, you get a whole number. Now, if we're multiplying a 2 by that, that's going to multiply each point's y value by 2. So the y value was 1, now it's 1 times 2. The y value is 2, now that's 2 times 2. 4. And so on and so forth. If 1, 2, 3, 4, 5, 6, 7, 8, 9 would normally be 3, now we're moving twice that distance to 6. This is actually our first situation where there is no horizontal shift whatsoever. Making c equals 0 basically centers it right on the origin, and multiplying it by 2 makes each function jump up like that. So that's what this one looks like. If you plug in 1, that would indicate a horizontal shift right 1 unit. So you can just take this whole graph and say, okay, 1, 0 is now our origin. So you'd go over 1, and normally it would go up 1, but now it's doubling that. Same thing, 1, 2, 3, 4, up 2, but now doubling that. Or you can just look at it as, from the graph we just sketched, shift 1, shift 1, shift 1, shift 1. And then our last one, -2, means it's x minus -2, which is, addition. That means it's a left shift 2 units, and really not much of a difference there. But concept-wise, I think you guys can see how these functions relate to one another and how the shifts change things. So 17, checked them all off the list. Number 19 looks interesting. If I told you to totally ignore the c, I'm hoping that you guys would look at this and say, root 4 minus x squared. We talked about that the other day. It's a semicircle. True. But when you start throwing factors, multiples in front of the root, you don't just mess with like random points. You're messing with points that create radius values. Let me show you what I mean. So if you plug in a 1 here, anything times 1 is itself. So that definitely is a semicircle. Now in this case, semicircles have r squared minus x squared if it's centered just around the center of 0, 0. Centered around the center, duh, right? 0, 0 with a unit radius of 2. So 2 away from the origin. There's your semicircle. So that's when c equals 1. When c equals 3, you no longer have a semicircle. Because even though these are y values of 0, and 0 times 3 is just, still 0, this radius of 2 value has just been multiplied threefold. So it's going to be, it's 2, 4, 6 now. And if you just picked a random point anywhere here, so let's say at this value it's 1, now that value is at 3. and you get kind of an elliptical figure there. So yeah, putting a coefficient that's not 1 in front of there really changes things. All right, and then what does negative 2 do? Well, it just reverses things. It takes that semicircle radius of 2 and makes it go down to negative 4. And pretty much behaves in a similar way as this guy over here did. So this one now would be down negative 2. Yeah. So those are the 3 graphs combined. All right, let's talk about number 21. Now, x to the 2/3 power. Let's break that apart a little bit. First of all, if it's just x minus 0, then everything disappears, and it's just x to the 2/3 plus 2. X to the 2/3 is the same as saying we're taking the cube root of x squared. So the behavior of this function is, can you guys see that? I don't think you can see what I was writing down. There we go. X to the 2/3 is the cube root of x squared. X squared makes everything positive inside this cube root. Cube rooting it keeps it positive. So the first thing that this tells us is anything that's bounded by a 2/3 exponent is automatically propelled above the x-axis. Now, you can shift it up or down, so it can go below the x-axis, say if you threw a negative out front and flip it, or shift it down. But at this point, it's not going below this point. If we plugged in some values like 0, you get 0. If you plugged in 1, 1 squared is 1. The cube root of 1 is 1. But then think about the negatives of this too. You plug in negative 1, square it, you get 1. Cube root of 1, 1. And the pattern is, it tends to kind of float upward, almost like, you know, when you were a little kid and you drew seagulls, it kind of looks like a seagull type graph. I think I might have pushed it up a little bit too quickly here. But that's basically what it looks like. And then if you put the plus 2 on there, as number 21 has it, yeah, shift up 2. 1, 2, 2, 2. These points behave in that way. So, you know, if you have a calculator with a table function, it'll kind of show you the exact points as you move out. Like if we took the cube root of 2 squared, it's going to be a different point than maybe what I was plotting. So I'm trying to think of points that would give us, when you square it, you get a perfect cube besides 1. So like if you square 8, you get 64, which the cube root of that is 4. So if we went out 1, 2, 3, 4, 5, 6, 7, 8 units, square it, you get 64. All right. Cube root of 64 is 4. Over 8, up 1, 2, 3, 4. Plus the 2 shifted up. We know that this is a point on that graph. So 8, 7, 6, 5, 4, 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8. And it's symmetrical. So there's where c equals 0. And c equals 4. Hopefully you guys are anticipating this. It's just going to shift. It's just going to shift right 4 units. And then the negative 3 shifts it right, left 3 units. All right, so that's that. Okay, do I have enough time to do that one? I'm gonna try. Go to 23. There's H, there's letters through H. Let's give it a try. So here's our original function. Looks kind of like a parabola. They say that the domain of this function is from 0 to 4. Sketch the graph of the equation if it's looking like this. So a function inside the parentheses versus outside the parentheses versus multiplied by something at the actual part of the function is really significant. Inside the parentheses indicates a horizontal shift, which makes total sense when you consider how parabolas work. The horizontal shift is inside the parentheses. How circles work. The shift is inside horizontally in the parentheses. How roots work. I could keep going with this. Okay. So this is just shifted left 3 units. This is shifted right 3 units. This is shifted up 3 units. And this is shifted down 3 units. So hopefully that's giving a pretty clear picture of how this is working out. If you threw a negative 3 out front of this, what does it do? Well, again, it multiplies every single point that you initially plotted by 3. So they're going to make a skinnier graph, and it's going to be inverted downward. So if you had the point 1, 1, that point is now 1, negative 3. It's basically 3 times as skinny. If you threw a negative 1/3 in front, it's going to multiply, it's going to multiply each point by negative 1/3. So this 1 is 1. It's going to be 1 is now negative 1/3 of a block. Everything's going to become wider. In fact, it should be right here. And then you can mix and match a few things. This one will shift it left 2, down 3, and flip it over the y-axis. Over the x-axis. But I'll leave G and H for it in class if you really want an explanation for it. So, yeah.